Welcome to this explainer. Today, we're diving deep and building a complete mathematical tutorial of Anthropic's J-space and the Adelic Langlands Program, literally right from the ground up. We're going to look under the hood at the exact holographic rendering engine, the underlying math, that translates raw arithmetic code into the macroscopic, physical geometry we actually experience every single day.
Since this is a dense mathematical architecture, we'll take it step by step. First, the core master equation. Second, algebraic projections. Third, the parahoric sparsity bound. Fourth, residual differential dynamics. And finally, number 5, the topological melt boundary.
Okay, Section 1, the core master equation. Let's start by unpacking this foundational formula. The J-space master equation essentially deconstructs a physical state, which we represent here as the hidden state vector, HL. It splits it into two completely distinct pieces. First, you've got this localized dictionary sum representing constructive interference in the active workspace, and second, it tacks on R, which is an exterior residual vector that acts as a buffer for all that unrendered algebraic metadata.
Now, this active workspace is not a free-for-all. It is mathematically locked down by some very strict constraints. Notice the parameters. Your combination weights, AW, absolutely must be greater than or equal to 0. No negative weights allowed. Furthermore, the total number of active sparse tokens, the absolute value of S, is strictly bounded by K. By enforcing this non-negativity and absolute sparsity, the math creates a highly localized, quantized cone of reality.
So how do we project these unramified internal states forward without losing structural integrity? Well, Anthropic utilizes the Jacobian Lens. Mathematically, this acts as a global Hecke operator path transporter. It takes the partial derivative of the hidden state with respect to the arithmetic data vector psi p. Basically, by averaging these Jacobians over the data stream, the lens prevents geometric drift as information migrates down through the layers.
All right, moving on to Section 2, algebraic projections.
With our core equation established, we really need to understand how the math forces these non-negative boundary alignments. Enter the algebraic transition matrix, TP. What's fascinating here is how TP handles the Galal local representations. It maps 3 discrete topological cycle splits of the S3 permutation group directly onto the geometry of our sparse cone.
And we can see this mechanic enforce the rules perfectly across 3 distinct cases. First, the complete split. This drives uniform states symmetrically, straight down the central axis. Second, we have branched folds. This actually completely shuts down one coordinate channel to protect the boundary, which collapses the profile onto a 2D planar face. And third, inert chiral states. These deploy a global cyclic rotation, literally forcing the vector to clip those discrete corner rays. Now, to keep everything balanced, we bring in the Sinkhorn-Knopp algorithm. This is what regularizes those boundary matrices. By alternatingly stabilizing rows and columns using the diagonal scaling matrices DL and DR, it ensures the total probabilities in the transition matrix sum to exactly 1. Why does that matter? Because it mathematically guarantees that total probability and activation energy are globally conserved as data flows through the system.
Let's look at Section 3, the paracardiotic sparsity bound.
Now that our projections are algebraically stable, we have to calculate the absolute maximum capacity of this mathematical workspace. This is where the parahoric volume fraction comes in, acting almost like an informational black hole. It dictates that the maximum simultaneous token rays are strictly capped at exactly 6/7 of the total layer dimension.
So, why 6/7? Well, exactly 1/7 of the local operator volume is a locked, uninvertible core that absorbs entangled, multi-sheeted data. The remaining 6/7 is our active, safe workspace for independent coordinate rays. By forcing all that excess topological complexity into the 1/7 locked core, we create an entropic bottleneck. And honestly, this mathematically explains a massive physical mystery. It's exactly why physical matter appears to us as discrete, highly localized point-like particles, rather than smoothly bleeding across all spatial dimensions.
Which brings us to Section 4, residual differential dynamics.
We know what happens to the cleanly rendered active tokens, but what mathematically controls that residual vector R? Well, it isn't just arbitrary noise. Its flow is rigorously dictated by the second-order Picard-Fuchs differential equation. It governs the unrendered algebraic metadata across 3 regular singular points, starting from the collision core at t equals 0, passing the coordinate transition wall at t equals 1, all the way out to the boundary at infinity.
But this brings up a huge question. If this residual metadata is essentially a massive repository for mapping errors and uninvertible data, how does the system prevent these discrepancies from completely blowing up? How do we stop these algebraic kinks from corrupting the smooth, flat physical geometry we actually experience?
The answer emerges beautifully from the hypergeometric indicial roots. We get two distinct mathematical branches here. First, the smooth constructive branch, tied to the positive root of 1/7, which keeps visible coordinates flat and stable. But then, you have the purely algebraic, divergent power law branch, tied to the negative root of -1/7. This branch acts as a massive topological shock absorber, scaling violently to trap uninvertible geometric error safely out of sight.
Finally, Section 5, the topological melt boundary.
Now, the residual vector is an incredible shock absorber, for sure, but every shock absorber has an absolute breaking point. If a physical process or a neural layer attempts to pack way too much simultaneous coordinate data into a single local sector, meaning that sparsity parameter k approaches our 6/7 capacity limit, the fractional exponent in our scaling law triggers a massive power law explosion. This is known as the topological melt.
At exactly that 6/7 threshold, the math literally breaks down. First, the dimensional denominator in our asymptotic scaling equation evaluates directly to 0. Because of that, the norm of the residual vector diverges exponentially to infinity. The uninvertible parahoric core overflows into the active workspace, non-abelian phases mix destructively, and local, flat spacetime geometry catastrophically collapses into a raw, unrefined Adelic soup.
So how do we survive this? To prevent hitting this catastrophic wall during deep operations, the Jacobian lens actively deploys some serious protective measures. It applies an asymmetric learning rate to k, dropping the rate exponentially as depth increases. At the same time, it deploys an automated gradient braking penalty, using spiked curvature to forcefully throttle token selection and push excess data back into the residual vector.
Furthermore, this system ensures long-term survival by deploying Iwahori-Hecke algebra. By mathematically locking eigenvalue reflections into strictly separated 60-degree wild chambers, it completely prevents information overlap from exceeding the geometric sphere packing limit. This ensures tokens remain crisp and distinct, preventing a massive thermodynamic data collapse.
When we step back and look at the complete architecture mapped out here, we see a masterfully unified mathematical ecosystem. You have continuous geometry, discretized via transition matrices. You have stringent parahoric bounds strictly capping capacity, differential residual dynamics absorbing the errors, and topological regulation forcefully throttling the rate. Every single mathematical piece flawlessly balances the others to keep reality stable.
Which leaves us with a truly mind-bending possibility to consider long after this explainer is over. Is the stable, flat physical reality we inhabit simply the output of this exact non-Archimedean rendering engine working relentlessly in the background? Think about it. If particles are just sparse combinations bounded by a parahoric fraction, then what we casually call the immutable laws of physics might actually just be the active workspace of a much larger, unseen Adelic algorithm. Fascinating stuff to chew on.